In this video, we are going to apply transformations to quadratic functions. Before we look at an example to graph, let's recall that the equation of a base quadratic function is f of x equals x squared. So to get to the general form of the quadratic function, recall what we do is we replace x with b x minus h. Because our quadratic function is being squared, the x value is being squared, we're going to put b x minus h in another set of brackets and square that. Then we are going to multiply by our a parameter in front of the bracket, and we're going to add v at the end. So whenever we want to discuss transformations of quadratic functions, it needs to be in this form. So let's look at this example here given, and it is in this form. So we are now able to identify and describe the transformations. So outside of the bracket here we have a 3. So that means our a value is 3, and because it's multiplying the brackets, that means there is a vertical stretch of factor 3. Next, we go inside the brackets. This 2 is inside, it's being squared. So this is now in the bracket of lies. So our b value is 2, however, that means there's a horizontal compression of a half. It's the opposite of what it looks like. So it's a 2, so it's a compression of a half. The negative 5 is also in the brackets. So again, it's the opposite of what it looks like. So we're subtracting 5, which means that h is 5, which means there's a horizontal shift 5 units to the right. And then negative 9 is outside the brackets, and it's as it looks. So v is equal to negative 9, and that means there is a vertical shift 9 units down. Before we move on to graph this function, I just want to take a minute and just talk about what would happen if the inside of the bracket here, this 2 bracket x minus 5, was expanded. So it would look like 2x minus 10. That whole bracket would be squared, multiplied by 3, and minus 9. So the only thing I did was expand the bracket of lies. So it looks like 2x minus 10 instead of this factored form of 2x minus 5. This is not in the form that's required above to identify the transformations. You would get 3 of them correct. You get the a value of 3 still, the v value of negative 9. You get the b value of 2. However, if you did not factor this, you would have said that the h value is positive 10. Really, the h value is positive 5. So you must remember that inside here, the bracket of lies, it needs to be factored. So to graph from transformations, we follow the steps here on the side. Step 1, we graph the base function. So the base function is x squared, so this is graphed here. Just be careful of the scale here. On my horizontal axis, 2 boxes represents 1, and my vertical axis, 1 box represents 1. So just be careful with that. But as you can see, my vertex of this parabola is 0, 0, and then when I went to the right one, I went up 1. I went to the right one again, I went up 1, 2, 3. Go to the right one again, and you go up 1, 2, 3, 4, 5. So we're going to use this base parabola to then apply the transformations. So now I'm ready for step 2. In step 2, what we do is we apply the a and b transformations. So we're going to apply the 3 for a, and we're going to apply the 2, which is our b value. So I had Desmos do this for me, just so it would be easier and hopefully more clear to follow this on the video, but I will explain how Desmos got this new graph. So the red graph was my base function, y equals x squared, and then this blue graph is when I applied the 3 and the 2. So the equation of that would be y equals 3 2x squared. I have not applied the negative 5 or the negative 9 yet. That's going to be my step 3. So that is not part of this equation. So I'm going to use a few points on my base graph and then apply these two transformations. So remember the 3 is my a value, so it affects my y variables by multiplying all my y coordinates by 3. The 2 affects my x coordinates, and what I'm doing is dividing all my x coordinates by 2. So let's apply that to 0, 0. So my x is 0, so divide x 0 by 2, which is still 0. My y is 3, multiply it by 3, so it's still 0, 0. So this point actually does not move when I apply my stretch and compressions. The point 1, 1, my next point here, I am going to multiply the y value by 3, and I'm going to divide this 1 by 2. So that means the x value of 1 now becomes x value of a half, and the y value is now 3. So there's 1, we're already at 1, 2, 3. So right here is going to be my new coordinate, my transform coordinate right here. So again, this graph is compressed by half horizontally and it's stretched by 3. It doesn't mean we move up 3 units because then we'd be up here. It means this 1 is now multiplied by 3, so we're now at 3. So this next point, 2, 4, my x value is 2. I'm going to divide that by 2 to get 1. So I'm now here at 1. So I've gone half the distance away from my y-axis here. And then my y value is 4. To get my new y value, I'm going to triple it. So 4 times 3 is 12. So I'm going to move up here to 12. And you can see that's on the blue parabola. So I'll just mark that new point. And again, you can see that my graph is compressed horizontally. I've gone half the distance to the right, and I've tripled the distance stretching up vertically. The point 39 looks to be above the graph, so I'm not going to be able to show that, but we already have 3 points on the right side. That's enough. And then you can just, we know from parabolas, these points will just be reflected on the other side. But if you don't see that, you can still apply these transformations. So at this point, negative 1, 1, the x value is negative 1. Negative 1 divided by 2 is negative a half. So instead of being here at negative 1, you're now at negative a half. And then the y value is 1. 1 times the 3 is 3. So you're at 1, and then your y value is going to be at 3. So again, you're here, and you can see that your points are the same distance away from the axis of symmetry. So now we are ready for step 3, where we apply the h and v transformations. So again, h is positive 5, and v is negative 9. So that means we're just going to take the blue parabola, so the one where we performed the stretches and compressions, and we are just going to move those key points. So I'll start at the origin, and I'm going to move 5 to the right, 1, 2, 3, 4, 5, and then I'm going to go 9 down, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I end here. That's where my vertex is. Next, this point here at 1, 3, I'm going to go 5 to the right, 1, 2, 3, 4, 5, and then down 9. So I end up right here. And then I'll do one last point up here, this 2, 12. Again, I'm going to go 1, 2, 3, 4, 5 to the right, and 9 down, 1, 2, 3, 4, 5, 6, 7, 8, 9. And you can see I'm right on that green parabola. So just make sure you label with the equation of the function that you were asked to graph. And we need to do step 4 even though it was deleted from the steps box. So step 4 is just you check a point on your parabola to see if it works. So let's see. a nice easy point is this point here at 5, -9. So what we do with that is we substitute in x is 5 into the function that we were graphing, and we should, when we put in 5 into this equation, we should get a y value of 9. Sorry, -9. So we're going to put in 5 for x, so we get 3, 2, 5 minus 5. And now we're going to simplify that. So 5 minus 5 is 0, times 2 is 0, square 0 is 0, multiplied by 3 is 0, and then you subtract 9. So we do get -9. And that will work for any value of x you choose on your final graph. If you put in the x value, you should get the correct y value. In grade 10, you looked at transformations, but you only looked at a values, h values, and v values. You did not have any b values, and I'm going to show you why now. To do that, I want to find another equation for this green quadratic function that we just graphed, using the knowledge that you have from grade 10 of finding the vertex and the step pattern. So we have already identified the vertex of 5, -9, and the step pattern, what we're going to do is move 1 unit to the right and count how many units up we went. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we went up 12 units, which means that the a value is 12. So our function could be written as f of x equals 12 x minus 5 squared minus 9. So here we see that the b value is 1, which is the case for every quadratic function that you looked at in grade 10. So we now have two different equations for the same function. The first one had an a value and a b value, and the second equation only has an a value. So in grade 10, you did not need to talk about b values because you could also write the equations of quadratic functions in terms of a values only. And this really is showing us that vertical stretches and compressions and horizontal stretches and compressions can mimic each other. They can imitate each other. So the final thing I'm going to do is just algebraically prove how that is possible. So remember, inside my bracket of lies, which is 2x minus 5, that whole big bracket is being squared. So that squared applies to the 2 and it applies to the x minus 5. So I'm going to apply that squared to the 2 and the x minus 5, and I get 3, 2 squared, x minus 5 squared, minus 9. So that is just 3 bracket 4 x minus 5 squared minus 9. So now these big square brackets are not needed because there's nothing on the outside of it. So I am now going to multiply this 3 times 4 together, and I get 12 when I do that. And then I have x minus 5 squared minus 9. So now this, when I applied that squared on my b value and then simplified it, I end up with that other quadratic equation. So that's an algebraic way of looking at both. So one thing you could do is, if you ever have a b value in your quadratic equation, you could algebraically change it so you just have an a value. However, you are not going to always be able to avoid working with the b values.